All right. Good morning, everyone. Welcome to Medallion Lecture session. Today, I am very excited to chair Professor Rina Barber's Medallion Lecture. So let me start with giving a short introduction of Professor Barber. Professor Barber is a Lewis Block professor in the Department of Statistics at University of Chicago. She is one of the very best statisticians, and she has a wide research interest. She has been working on developing and analyzing estimation, inference, and optimization tools for structured high-dimensional data. Data problems such as sparse regression, sparse long-parametric models, and low-rank models. Her research has been highly fundamental, original, and impactful. Professor Barber's research achievements have been well recognized by the society, and she's the recipient of many very prestigious awards. To name just a few, because of time constraint, she was the winner of the 2020 House President's Award, one of the highest honors in the field of statistics. She was also awarded the Peter Garvin Hall Early Career Prize in 2020, and she received the prestigious Sloan Fellowship in 2016. The list goes on and on. Each year, Medallion nominates 8 Medallion lectures in fields among IMS subject range. The award of a Medallion signals the honor inherent in being selected to give one of the lectures. This year, IMS awards a medallion to Professor Rina Foygel and IMS. Professor Barber to give a medallion lecture with a title, The Medallion Contribution, Exchangeability, and Beyond.
Okay, thank you very much. Thank you so much, Union, for the kind introduction, and thank you so much for the invitation to give this talk. This is a huge honor. I'm really happy to be here and to get to be here in person and get to chat with so many great colleagues. So today I'm going to be talking about distribution pre-prediction. I'm going to be talking about a couple of projects in this area, and I've been really lucky to work with amazing collaborators in this area. The work I'm going to be presenting today is joint with Emmanuel Kandaz, Aditya Ramdas, and Ryan Tishirani. So let me start by introducing the problem that we're thinking about. We're in a setting where we have supervised learning, so labeled data. We have XY pairs for our training data, and N will always be the sample size today. And then we have a test point where the X value is observed and the Y value is what we want to predict. So this is a prediction task. And in general, we would want to be able to do predictive inference that leverages the most powerful tools that we have. So the most modern, perhaps complex, perhaps not very well understood tools. We'd like to be able to use any model we like in order to fit to the training data, but then we would like to perform some inference and say something about how reliable is the prediction coming out of that model. So if we fit a model mu hat n to the entire training set, perhaps it does a good job, or perhaps it made assumptions that weren't quite true, and so it didn't do so well. How do we know how accurate that model will be in order to predict y? So mu hat of xn plus 1 is our prediction for the unknown yn plus 1. How big will that error be? And one thing that we can already know, even if there's no issues of non-stationary data or transfer learning, nothing like that, training and test data comes from the same distribution. We already know that overfitting is typically going to be a substantial issue, meaning that if I look at the training residuals here on the right-hand side as a measure of how good this model is, it will be overly optimistic, and my actual error on the test point, what I cannot see, is probably going to be bigger than the typical error on the training point. And so the problem of predictive inference fundamentally is to be able to do something that is more principled than this, that is able to say, okay, here is roughly how well I think I'm going to be predicting on the test data, given the model that I fitted to my training data. So if we run some algorithm of our choice on the training data and we get a fitted model, in some simple settings, we might just want a basic prediction interval that's centered on the predicted value plus or minus the margin of error. I'll just be talking about this simple setting. Of course, in other cases, we might want something that's not symmetrical, or maybe y is discrete or categorical, or something that's a little bit different. I'll just focus on this setting here to keep things more intuitive. So how do we decide how big that margin of error should be? So we've just said that we can't just naively use the training residuals because of overfitting, but maybe we could use a parametric model or something non-parametric with smoothness assumptions to give us some analytical form for how big that margin of error should be. Now, in lots of settings, we know, of course, that will work well, but if those assumptions aren't true, and if we can't reliably test whether they're true or not, then we're sort of relying on unseen conditions or untestable conditions in order for this margin of error to be wide enough and for our prediction interval to actually have the right, like 90% or whatever we want, coverage rate for the y value that we're trying to cover. So maybe we want to avoid assumptions, and so perhaps we could use something like cross-validation to tell us how wide this margin of error needs to be in order to get predictive coverage. And so the problem of predictive inference in this particular setting is basically like, how do we know how wide to make that in order to get the predictive coverage that we want? Okay, so to try to make our goals a little bit more precise here, what if we want to be distribution free? Meaning that no matter what model I use, no matter what assumption my model makes in order to fit NuHat to the training data, I would like the predictive interval to calibrate to the real distribution of the data and to give me the right coverage level. I'll write 1 minus alpha, oops, sorry. I'll write 1 minus alpha in the slides, but I'll just say 90% out loud to keep it simple. So how do we know that whether our model was right or wrong, we have some way of picking the margin of error so that we'll actually get that 90% coverage? So in particular, if my model was well chosen for the actual distribution of the data, my margin of error might end up pretty narrow. If the model actually fitted the data quite poorly, my margin of error should compensate for that and be pretty wide. I'd like a procedure that sort of adapts to whatever setting that we're in, so that regardless of the distribution, with no assumptions at all, we want that 90% predictive coverage. So that's the goal of the problem of distribution-free prediction. Now, of course, I could give you something trivially that satisfies that. The margin of error could be infinity, and my predictive interval could just be the entire real line. But obviously, this isn't informative. And so we want to trade off this validity with using the training data efficiently. We'd like to make the prediction interval as narrow as it can be, subject to what we need it to satisfy. So we want something that's precise at the same time as having guaranteed validity. Okay, so here's the outline of what I'll be talking about. First, I'm going to give some background on the conformal prediction framework, and then I'll talk about 2 projects with the collaborators that I mentioned, the Jackknife Plus, which is a new method for distribution-free prediction. And then I'll talk about conformal prediction beyond exchangeability. I haven't talked about this term yet, but basically I'll be talking about thinking of settings where the training data might not necessarily be from the same distribution as the test data. Okay, so a little bit of background. So first, what would we do if we don't want to rely on assumptions? Like, I don't want to use the formula from linear regression to tell me how to make my prediction interval, because what if the linear model is not correct? What do I do if I don't want to rely on assumptions, but of course I can't just naively look at the training errors to tell me how good my model is? The perhaps most well-known thing to do is to just use a holdout set. And in situations where the sample size n is very large, as is the case for a lot of big data settings, this is a perfect thing to do because we basically just sidestep the overfitting problem. But for situations where our sample size is smaller, so if we think of n being patients in a medical setting, and so n might not be very big, there's a trade-off here where we have issues of sample splitting, and we perhaps might want to move beyond a holdout set. But let's start with this as a sort of base method. So what happens for a holdout set? I split my data, my training data into parts, so let's say half and half. I use the first half to fit a model using whatever algorithm I like. Maybe my assumptions were approximately true, maybe they weren't. The holdout set will tell me how well I did. So I will then calculate the residuals on all of the data points which were not used in the training process. And then finally, I use those holdout residuals to tell me the margin of error for my prediction interval. So if I want 90% coverage for new test data, then I could just take the 90th percentile of my holdout residuals. Now, of course, we are assuming here that the test data is coming from the same distribution as where we got the holdout data. But aside from that, we can see that this should work no matter what the distribution of the data is, because if my model was wrong at the first stage, my holdout residuals will be large and will correct for that at the second stage. So what can we say about this theoretically? And we can immediately see that here we're using these n/2 many holdout points as a sample from some hypothetical population, where the population is, what errors would I make when I try to predict test points drawn from the distribution? So here, if n is large, and so the holdout set, perhaps size n/2 is also large, that should be fine. This doesn't exactly yet tell us what happens at the finite sample level. So to see that, let me take a step back for a moment and give some background on the conformal prediction framework. So the key reference for this framework is the 2005 textbook by both Gammerman and Schaefer, Algorithmic Learning in a Random World. And in this textbook, they lay out the idea that just by using exchangeability of the data, so for example, training data is coming from the same distribution as the test points that I'm trying to predict. With only that assumption, there's a ton of statistical inference that can already be done. So this is without asymptotics. This is without any assumptions on the distribution that the data is coming from. So the ideas in this book date back to work by Vovk collaborators in the late 90s. For example, this Gammerman, Vovk, and Vapnik paper, Learning by Transduction from '98. And more recently, in the last 5 to 10 years, there's been a ton of interest in this framework in the machine learning community in addition to statistics. And I want to highlight this paper by Lay et al., Distribution-Free Predictive Inference for Regression, which continues to develop this framework for a lot of problems in statistics. So let's see now what the conformal prediction framework can tell us about the holdout set method. So in the conformal prediction world, sometimes the holdout set method is called split conformal prediction. We'll see where that name comes from in a moment. And there's one small modification that's happening here relative to the holdout set prediction interval 2 slides ago. So 2 slides ago, we said, how wide should we make that margin of error? Well, we'll just take our holdout residuals and take the 90th percentile of that list. Here we can see there's a small correction, which is instead of looking at 90% times n/2, the size of the holdout set, in terms of how far up the list you go if you rank the residuals from smallest to largest, there's this +1 correction, 90% times the size of the holdout set +1. So it's very slightly more conservative in the sense that in the ranked list of residuals, perhaps you went up 1 higher to define how wide should be that margin of error. And with this slight modification, Vovk et al.'s work proves that if the data come from the same distribution, so IID from the same distribution, or more generally, the data points are just exchangeable, then no matter what algorithm was used, the split conformal prediction method, so this interval here, satisfies 90% coverage, or 1 minus alpha coverage that we wanted. So this probability is taken over the new draw of the test point, xn plus 1, yn plus 1, as well as the draw of the training data. So this is a very remarkable result because this is finite sample. This says nothing about n having to be large. And of course, it also makes no assumptions about where the data came from, what that distribution is, or what was the algorithm that we used in order to fit that initial model mu hat on the first part of the training data. So this result basically tells us that we can already do distribution-free prediction using this holdout set method, as long as we make this +1 modification. So now let's see why it is that exchangeability is at the heart of these ideas and at the heart of this proof. So here's a quick proof sketch of that result. So if the data is exchangeable, then even after I train my model on the first half of the training data, the data points in the holdout set and the test point, so that combined collection of n/2 plus 1 points, holdout and test, those data points are still exchangeable with each other, since in the IID setting, they're still being drawn from the same distribution. What this means is that the residuals on the holdout points and on the test set, so what error do I make on the holdout points, what error would I make on the new test point, those residuals are all exchangeable with each other. Now, even if the data is IID, these residuals are not independent because they're all using the same trained model, but they are still exchangeable. And in other words, they could occur in any order. The test residual Rn plus 1 is equally likely to be the smallest value or the largest value or anything in between. So in particular, what that says is that if I take the 90th percentile of that list, then any one entry in the list has a 90% chance of lying below that. So if I take the 90th percentile, that should be an upper bound on the error that I make on the test point with 90% probability. Now, if we just rearrange this event that's written in purple here, this is the same as the events that the sort of adjusted quantile calculated on just the holdout set is an upper bound on the error that I will make when I try to predict the test point. And that's the same as the event that my prediction interval successfully contains the value of y, which I am trying to predict. So in other words, the reason there's this +1 correction in this finite sample definition of how do you calculate a quantile from a list of values, that reason is because under the hood we have exchangeability, and that exchangeability applies to a list of n/2 + 1 many points, the holdout points and the test point. So we can see why exchangeability brings us from a very intuitive method that seems like it will hold perhaps only asymptotically to something that holds in the finite sample setting with no adjustments needed. Now, split conformal prediction already gives us the validity that we want for distribution-free prediction, but it does have the drawback that if n is small, I might have a much less accurate model fit than you had because it was only allowed to see half of the data or some fraction of the data. So now we come to what is often called full conformal prediction, which is this remarkable idea that you can actually use the entire data set and still get valid prediction. So even though every point was used for training the model and we would think we have an overfitting issue, it's still possible to get distribution-free prediction. So this is the full conformal prediction method of Volk-et-al. So here's the idea. I'm going to start by showing that we're doing something imaginary, which we can't do. So this is just hypothetical. So imagine that we could actually see the test point. Of course I can't, because that's what I'm trying to predict. But if I could fit a model mu hat n + 1 to this combined data set of n training points plus 1 test point. And then I'm going to compute the residuals for the training point and the training points and the test point. And of course I do have overfitting because the residuals are computed on data points which were used for training. But the interesting thing is I have overfitting on my training points, but I equally have overfitting on the test point, because in this hypothetical scenario, the test point was also used for training. And so the training residuals actually are representative of how big the test error should be, because overfitting applies just as much to the training data as to the test point in this hypothetical fitted model. In other words, the training and test point, the training points and the test point are being treated exchangeably here. And so it's just as likely that the test residual lies at the bottom of the list or at the top of the list. Or in other words, if I take the 90th percentile of my list, there should be a 90% chance that the test residual is not higher than that value. So now what do I need for that to be true? We need the data points to be exchangeable, like they come from the same distribution originally. Otherwise, the test residual might be bigger just because it came from a different distribution. And we also need that the algorithm treats data points symmetrically, because if you have symmetric data, but the algorithm treats the data points differently, sorry, if you have exchangeable data, but the algorithm treats data points differently, we might no longer have exchangeable residuals. So for example, I am allowed to use least squares. I'm not allowed to use something like an autoregressive model that treats the last data point differently than a data point in the middle of the list. Okay, now, of course, this gives me a sort of measure of like how big my margin of error should be, but it's not practically useful yet because I need to pretend that I observed the value of y, which I didn't actually observe. So now here's how the method works in practice. We're going to pick a value little y, which is a guess for the actual value yn + 1, which I'm trying to predict. And we know that if my guess was correct, so if I happened to guess the exact right value, then there should be a 90% chance that this event holds. So to invert that statement, I can tell that my guess was a good guess and is a plausible value for yn + 1 if that event holds. And so I can use that event as a screening procedure to tell me which guesses are about right for plausible values of yn + 1. So finally, the definition of the prediction interval is that we run this for every possible value little y, so potentially every value in the real line, or in practice on a grid. And then we check whether this event holds after running the procedure for a particular little y. And then we put it in the set or remove it and leave it out of the set, depending on whether the event holds or fails. And then we repeat this for all possible values of yn + 1, which we're trying to predict. Now, I can still call this a prediction interval, but actually in practice, it might not be an interval. It might be a set made up of a bunch of disjoint intervals, but oftentimes in practice, it still turns out to be an interval. So we can see from this construction that exchangeability of the data gives you exchangeability of the residuals. Exchangeability of the residuals gives you this fact that this statement has a 90% chance of holding when I plug in the right value of y. And as soon as that's true, then the true value of y lands in the prediction set and I have coverage. So this idea based on exchangeability gives us the result for full conformal prediction, which is, again, just like for split conformal, we have distribution-free predictive validity. But now this is no longer paying the price of data splitting because all of the data points, all of the training data were used in order to fit our models. And so full conformal prediction is able to get distribution-free predictive validity without having to pay the price of data split. Okay, so with that background, let me now move on to the jackknife plus, which is a new method that also provides distribution-free predictive inference. And to motivate it, let's compare actually what we have so far with split and full conformal. So for split conformal, it's computationally inexpensive because you only have to fit one model. So if I'm running an expensive deep learning procedure, I only have to run it once. But the cost of that is that it's trained on only a fraction of the available data. And so my resulting prediction intervals might be wider because they have to compensate for a less accurate fitted model at the center of that prediction interval. On the flip side, full conformal should in general give you much narrower intervals, at least in settings where the sample size n is not too big, and so gaining in sample size gives you a big gain in accuracy. But on the other hand, we need to, at least in theory, call the algorithm A infinitely many times if y is real value, because I need to rerun it for every guess, little y, of the possible value yn plus 1, which I'm trying to predict. So we might think that perhaps something in between these would be useful, to have a compromise between the precision of the answer versus the computational cost. And so cross-validation gives us a natural choice for where to look. So let's say that we do leave one out cross-validation. What would this look like traditionally? So leave one out cross-validation is also sometimes called jackknife, so I'll use that term here. So typically what we do is that we center our interval on the predicted value, which is fitted to the entire training data set, but I don't want to use the training residuals to tell me my margin of error because of the overfitting problem. And so instead we're going to use these leave one out residuals, where for each training point, I remove it from model training and rerun my algorithm. And then I get the residual after it's been left out. And so these residuals do not have any overfitting. I'm looking at the residual on data point I when my model did not train on data point I. And so intuitively, this should give us the right margin of error since we've moved away from the overfitting problem. And in practice, this generally works very well. But there are no distribution-free guarantees for this procedure. You can get guarantees under some mild assumptions. So in particular, Steinberger and Lieb prove that you do have asymptotic predictive coverage if you choose an algorithm which satisfies a condition known as algorithmic stability. What that condition means is that if I train my model on the entire training data set versus if I train it on the same training data set but with 1 point pulled out, it should give me roughly the same predicted value at my new test point xn plus 1. So in other words, removing 1 point for training shouldn't change much at prediction time. Now, this condition is something that sounds like a condition on the algorithm, but it's actually a condition jointly on the algorithm and the data distribution, since we need this to be true when the data is drawn from the unknown distribution with high probability. So this is a mild condition, but it's not quite distribution free. And our starting point for this work on the jackknife plus is to ask, what can we do with this method? How can we study it in a truly distribution-free context? So before I show you our method, let me show another representation of how to define the jackknife or leave one out cross-validation interval. So let's say that we take prediction intervals, one for each training point, where I center it at the predicted value, fitting the model on the entire training data set. But then I just use a single leave one out residual to tell me how wide that prediction interval should be. Obviously, this is extremely noisy, but let's imagine that we do this. And we stack them all up vertically, and the centers all line up because the centers are the predictions, which are all the same. It's only the margin of errors that are different since they use the different leave one out residual. And then finally, to get my final interval for jackknife, I'm going to draw these endpoints of the interval, the dotted lines. I'm going to make them far out enough so that 90% of these arrowheads lie inside the dashed lines and 10% or alpha fall outside. So here, the purple stars are marking which of the intervals fell outside the lines, and that should be 10% of 10. So this is an equivalent definition of the exact same equation from the last slide. And so now that we have this picture, that'll make it easier to define our modification, which we call the jackknife plus. So for the jackknife plus, the picture looks very similar, but at the center of each of these individual intervals is the leave one out prediction. So for training data point I run the leave one out model that leaves out data point I, and I use that both to get my leave one out residual, Ri, and also to give me a prediction for the test point. I then will center my interval at that leave one out prediction, and then the margin of error is the same as before. So if you compare the left to the right picture, you can see the centers have moved a little bit, but the width of each of these intervals stays exactly the same since they're using the same leave one out residual. Now, finally, I'm again going to just draw these dashed lines to be exactly as far out as they need to be so that 90% of the endpoints lie inside the dashed lines and 10% fall outside. Now, when are these two going to be similar versus highly different? If the algorithm is stable, then the prediction that I get with the full training data versus with a leave one out version of that same training data set, those predictions should be nearly the same. And so these centers in the new interval, the jackknife plus, should just be like a very slight jittering of the shared center for the picture in the left. And the interval that you get at the end should be basically the same. But if you have high instability and these centers move around a lot, then we could get a very different answer. And this is exactly what we want because Steinberger and Leaves' work tells us that jackknife is already doing the right thing when algorithmic stability is present, but it may not have coverage if algorithmic stability is not there. So this is what we want. We want a method that basically sort of keeps the strength of jackknife if you have stability, but gives you something different that will hopefully regain coverage if you do not have stability. So here's the same definition in an equation, and the only difference between jackknife and the new jackknife plus is that we use these leave one out models rather than the full trained model in terms of where we predict. I'll also just mention that in our paper, we have an extension to k-fold CV rather than leave one out CV if we don't want to fit that many models. We call that CV plus. And I'll also say that CV plus is very closely related to both cross-conformal methods. So this work is very much building on those methods there. Okay, so going back to our comparison, we can see that jackknife plus and more generally k-fold CV plus are giving us sort of an interpolation between the computational cost versus the sort of efficient use of the data that we get when we compare split conformal versus full conformal. But we haven't yet seen any of the theories. So what does this actually give us? Can we say something distribution free? And what our result says is that if, again, the data come from an exchangeable distribution, so for example, IID from an unknown distribution, and also, again, we assume that the algorithm treats data points symmetrically, then the jackknife plus does have a distribution free guarantee, but it's not quite what we expected. It's actually a lower bound of 1 minus 2 alpha coverage rather than 1 minus alpha. So we asked for 90%. In practice, we generally see 90%. The theory tells us it might go down to as low as 80%. So we think of this as sort of like insurance because the worst case scenario doubles the error, but the coverage can't go down to 0, for example. But in practice, we do see the right level of coverage, and also we can prove that asymptotically you get the 90% or 1 minus alpha coverage if we assume algorithmic stability. So if we have the same conditions as jackknife, then we still get the right coverage level. Okay, so in just very briefly, I will just mention sort of the key idea at the heart of the proof for this. And what I found interesting for this problem is that it's not immediately obvious how exchangeability is going to play a role. Because when we look at what jackknife plus is constructed with, it's constructed with many leave one out models. And that collection of models does not treat training data and test data equivalently. The test point does not appear in any of those fitted models, whereas each training point appears in all but one of those models. This is different from full conformal, where the idea is that the model is treating training and test data the same. But under the surface, this actually turns out to still rely on exchangeability. And the reason is that we can embed the collection of models that we actually see for jackknife plus into a larger collection of models which are exchangeable. So imagine that I have my training and test data combined, just like for full conformal. So I have n plus 1 data points. But now what I do is I fit all of the possible leave 2 out models. So that is sort of an array of models. And that array treats training and test data symmetrically because it could be a training point that's left out. It could be the test point that's left out. Now, of course, if one of the 2 points that I leave out is the test point, and then the other one is one of the training points, that's exactly the same as the leave one out models used by jackknife plus. And so that's how jackknife plus kind of lies inside of a larger exchangeable problem. To wrap up with jackknife plus, let me just show one slide with a quick simulation result. So this is in a linear regression setting, both low and high dimensional. And we're using ridgeless regression, so ridge with the penalty parameter going down to 0. This was studied for interpolation learning by Hasty et al. And what they find is that it's only when the dimension is approximately equal to n, when you have an IID Gaussian design, that you get algorithmic instability. If the dimension is low, then of course it's stable, that's just least squares. If the dimension is much larger than n, then that provides implicit regularization and it's stable again. But when d is approximately equal to n, we have instability. And what we see in that regime where d is approximately equal to n is exactly where jackknife and jackknife plus diverge. Jackknife plus keeps coverage, whereas jackknife actually loses coverage pretty substantially just at those few points where d is equal or almost equal to n. On the other hand, everywhere else where d is low or d is high, so when the algorithm is stable, jackknife plus has basically not changed what we get from jackknife. We have the same coverage, which is the 90% that we want, and basically the same width as well. Okay, so now let me switch gears and talk about conformal prediction beyond exchangeability. So everything I've said so far uses the word exchangeability on basically every slide, and we can really see that it's completely at the heart of all of these methods. So why is that? So there's two ways that exchangeability comes in. One is that we assume the data is exchangeable. So for example, IID from a shared distribution. But the second is that we also assume the algorithm treats data symmetrically, so that even after I observe the output of running the algorithm on full conformal, say, for training and test data, even after that model is fitted, the data is still exchangeable because the model uses the data symmetrically. It doesn't tell you anything about which data point is which. So how does this work? Let's illustrate this in a picture. So here's all my data, training and test, and I'm color coding from light blue to dark blue to go from the first data point through to the last data point, which is the test point. The circle indicates the test point. Now I'm using the algorithm, which is least squares. So here's the fitted line. And let's say I only show you the figure on the right-hand side where the color coding is gone. Now there's no information to tell you which data point is which. And so the test point is equally likely to be any one of the n+1 points in this picture, even after you observe the fitted line, since the fitted line treats the data symmetrically and carries no information about which is which. In particular, if we then calculate the residuals for all of those n+1 data points, any one of those residuals could be my test point error. We don't know. It's just a uniform distribution. And this is at the heart of the full conformal proof. But what are the challenges in practice? So first, data might not be exchangeable. It could be non-stationary because distributions might drift over time. Or maybe it is stationary, but there's dependence over time, and that makes the exchangeability assumption fail in a different way. The second thing is that we might want to use an algorithm which doesn't treat the data symmetrically. Now, of course, this sounds a little odd because, like, don't we choose the algorithm? If we know it has to be symmetric, why wouldn't we just choose one that's symmetric? But the thing is that we would like distribution-free prediction to not carry a cost of accuracy. So if the best model for my data, if I believe that that's an autoregressive model, I'd like to be allowed to use it and still get distribution-free prediction guarantees. So even though the second assumption is under our control, we would still like to relax it. So let's see in our picture why we have a problem. So the first issue is distribution drift. We have the early data points, let's say early in time, up in this region in the top left, and the later ones down in the bottom right. The algorithm is still symmetric because it's still least squares. Now, if I show you this picture on the right, distribution drift means that it's not equally likely for the test point to appear anywhere. In particular, the test point is much more likely to be one of these in the bottom right. And we can see that those actually have larger residuals. So the 90th percentile of all the residuals in this picture is not going to have 90% coverage for the test point. On the flip side, if we do have exchangeable data, but we fail to have a symmetric algorithm like weighted least squares, here the algorithm is putting high weights on recent data, dark blue, and low weights on data in the distant past, light blue. So now if I show you this picture on the right, you can pretty much tell already that this point down here cannot be the test point, because if it were, it would have been given a high weight in the regression. And if it had been given a high weight, the line should be pulled down. So again, it's not true that the test point is equally likely to be any one of the points in the right-hand picture. So this is why the idea of exchangeability in the proof of full conformal and the related methods as well is really important. So our goal is to move beyond as much as we can, both of these assumptions, to allow for non-symmetric algorithms and to also have a coverage guarantee that's still exact and finite sample if the data is exchangeable, but that gives us some control of how much coverage is lost if we have some mild violations of exchangeability. Okay, so I'm going to present our method 2 times. First, when the algorithm is symmetric, just to start with a little bit more of a simpler case. And then in a minute, if the algorithm is non-symmetric, then the method needs to be modified a little bit as well. So this algorithm here looks exactly the same as full conformal, but the difference is that after I fit my model to the training and test data, where that value little y is like my guess for the test value of y, I compute my residuals. Now there's something different. When I ask, is this value of y plausible? Or equivalently, what I'm actually checking is the test residual in the bottom 90% of all of my residuals? Instead of treating that as sort of a list where each residual is equally likely to be the test residual, I'm going to put weights, wi, on each of my residuals. So these weights are chosen in advance. And the example we should keep in mind is just distribution drift over time, where I believe recent data is more representative of what I'm about to see at test time, and data in the distant past is perhaps not so relevant. And so we could have weights that decay as you move back in time, higher weights for recent data points. So when we do this, this is the only difference. We just calculate this quantile in a weighted way. And then again, the prediction interval is just computed by scanning over all possible values of y and checking whether this event holds or doesn't hold. So just informally, let's see how this helps us with the first problem, which is that the data may not be exchangeably distributed. And again, we'll be in the example where we have distribution drift over time. So this is just repeating the picture we already saw. Again, if the more recent data is more likely to be in the bottom right, then even when the data labels are removed, you can see that these points in the bottom right are more likely to contain the test point. And so the residual for the test point, my error for the test point, is more likely to be one of these large values and less likely to be one of these small values. Now, if I add weights where I put larger weights on recent data points, now the picture looks more like this, where now I'm thinking of the test point as a draw from the weighted empirical distribution of my training and test data, where the highest weights are put on the more recent data points, which have large residuals, and in this particular picture, and the smaller weights are put on the data points from the more distant past. And so now it is much more plausible to say that the test point acts kind of like a draw from this weighted distribution, since most likely I'll be drawing a point that was in the recent past when the data distribution is quite similar to what it is now at test time. Okay, now let's switch to what happens when we have a non-symmetric algorithm. And there's one more modification that we need to make, which is that when I apply my algorithm to fit my model to the training and test data, so perhaps it's like an autoregressive model, so the data points are treated in an ordered way. Before I do that, I have to draw a random index according to the weights that I will use later on in my quantile calculation. And then I swap the test point, I put it in position K, and the kth point, I put it in the position of the test point. So in other words, if your autoregressive model is treating the data as ordered, I perturb the data and then I feed it to that model. So once we do that, then the rest of the procedure is exactly the same. So the idea of this swap is that I'm basically hiding the test point among the rest of the data. So let's see again informally why this helps. So again, here's a repeat of the previous picture. If the data is exchangeable, so the dark blue and light blue are sort of just randomly mixed, but the algorithm is weighted least squares. And so we know, we knew initially this point over here cannot be the test point, for example, since a high weight on that point would have pulled the line down. So initially, if I use the original full conformal method, the non-symmetric algorithm reveals a lot about which of those points is more likely versus less likely to actually be equal to the test point. Now I'm going to do this with a swap. So here's my test point, here's my randomly chosen point number K, I swap them, then I run weighted least squares. What that means is that this K point now is given the high weight of the test point is now given the much lower weight of the K point. Now let's look at this picture on the right. Let's imagine that's what I gave to you. And now you ask, okay, could this point down here be the test point? Well, we can see from the weighted least squares line that that point could not have been given a high weight. Again, the line would have been pulled down. However, that tells us nothing about whether that point is the test point or not, because it's possible that this was the test point, but it was still given a low weight because it got swapped with something that came very early in time. And so what this swap does effectively is it sort of hides the location of the test point among the training and test combined data set. And so we avoid the problem that happened at the top, where you could kind of identify where the test point is likely to be. Okay, so I've talked about this with full conformal. I'll just mention that we can do the same type of idea with split conformal or with jackknife plus. So that's in our paper. I won't go into that here. Let me show you now what the theory looks like. And what the theory, again, the goal of our theory was to, one, allow for a non-symmetric algorithm, but still get distribution-free coverage, and two, have some kind of robustness to mild deviations from exchangeability, like recent data is pretty much exchangeable with test data, but data in the distant past is fairly different, and things like that. So here's the result we have. The first thing is that if the data is actually exchangeable, we get exactly the 1 minus alpha guarantee for coverage. And what that says is that basically full conformal still gets finite sample coverage with a non-symmetric algorithm once we've introduced this swapping trick. The second thing that we see is that if the data is not exchangeable, then we have this total variation term that controls how much of the coverage could be lost. So let's look into this for a moment here. So here, data with a subscript that says swap I means that I have my entire data set, x1, y1 through xn plus 1, yn plus 1, but I swap the test point with the ith training point. Does that still have the same distribution as the original data set? If the data is exchangeable, then swapping 2 points doesn't change the distribution, and this total variation is 0. If the data is not exchangeable, like if I have distribution drift, we might think that if I swap it with something recent, like 3 time points ago, that's not really detectable, and perhaps this total variation distance is still small. But if I swap it with a point, with a time in the distant past, then maybe the total variation distance is bigger. And so that's where these weights come in, which is, for example, with distribution drift, if the weights are only large for recent values of I, like I equals n minus 1, and the total variation distance is small at those recent values of I, that's a strategic choice of the weights that basically says, for the data points that I trust to swap with my test point and not be too different, I can give it a high weight and not lose too much coverage. So this reveals to us basically how we can choose the weights if we have some prior knowledge of which data points are likely to be a good representation of the tested distribution. Okay, so the last thing I want to show is a quick simulation. I'll compare full conformal with least squares. So this is a symmetric algorithm. Our new method with, again, least squares, where our weights decay backwards in time to try to correct for potential distribution drift. And finally, I'll also look at a non-symmetric algorithm, which is weighted least squares, which also uses more recent data more heavily, because that will hopefully give better prediction. So I want to mention that these weights are chosen without knowing the mechanism of distribution drift. We're just sort of ensuring against possible distribution drift, but we don't need to know what that distribution drift looks like. So in the top plot, what we see is the IID data setting. Basically, we did not need that insurance because the data actually is exchangeable. We see that the old method and the new methods get the right coverage level. We lose a tiny bit in terms of a wider prediction interval. That's because using the weights reduces the effective sample size. Now, if I do have non-exchangeability, either with distribution drift at the bottom or with change points in the middle, we can see that our new weighted method, non-exchangeable conformal, do a better job of maintaining the right coverage level, even when we have these challenges in the data. And we can also see in the right that using a non-symmetric algorithm like weighted least squares is a much more efficient use of the data we have because it's a better match to what's happening with distribution drift. And so we really see the gain here of allowing for a non-symmetric algorithm since the prediction intervals are much narrower. All right, so just to summarize, first, we saw that the jackknife plus gives us a compromise that's somewhere in between full and split conformal. It's a computational cost that lies anywhere in between that you like if you use k-fold CD plus. And it gives us a trade-off with a more efficient use of the training data that's available. And then finally, we saw that we can move beyond exchangeability. We can be robust to violations of exchangeability, and we can even allow ourselves to use non-symmetric algorithms, but still have exchangeability be at the heart of our theoretical understanding. What this tells us is that the conformal prediction framework can be applied with theoretical guarantees to a broad range of settings like non-stationary data, models with drift, and so on. So finally, I just want to say that this is a very exciting and open field, and we have a ton of open questions, and I'd be very happy to chat with anyone who's interested in this area. And thank you all very much.
Thank you, Rina. Thanks very much for the great talk. So we have time for questions.
Okay, thanks for this talk. I'm not really familiar with all the series quantities that you question, but it seems to me that when you're doing your analysis in a conformal prediction setting, that you're estimating the interval by assuming all of these
Thanks so much for the question. That's a great question. So yes, the predictions we actually do are on average over on average over X. And so if you want to use residuals locally, what you would be avoiding is a problem we could run into here, where the predicted 90% coverage holds on average, because it's 100% accurate for X's over here and only 80% accurate for X's over here. So there are a lot of methods that look at more localized versions of this, where you sort of use the idea that residuals with a nearby X, in some sense, nearby to your test point, are more relevant for telling you how accurate will the model be for this particular test point. In practice, in terms of the performance gain you can get, there's a lot of really nice results and you can get very far. The theory is a lot more challenging in terms of looking at trying to get these more local or locally conditional notions of predictive coverage. So the theory has a lot of really interesting results, but there's still a lot of open questions.
This is one thing So for starters, there's a distinction between algorithms that want to predict the cosmetric autograph model with a versus algorithms that sort of like have bypassed how to do them automatically. So if you're talking about that latter case, where like you just have to do it computationally, then you need all the data before you start. And then you need to collect the algorithm does to your data automatically. Now, I should mention that technically, these coverage characteristics are then on average over the draw of the data and the randomization of the algorithm. So I guess in principle, it's possible that for a particular draw of that shuffle, the coverage is lower than it should be. The algorithm compensation would be that to be Question about this algorithm. It seems like we are having a computer algorithm, and it seems like for a theorem, we have to be. What we have done is just look at the data first and then choose the algorithms to predict the roof or not.
That's a great question. Yes, to some extent, that's what we're trying to understand. So this work is assuming that the W's are fixed, and in particular, if you wanted them to be random, the current theory we have would allow for that, except that this term right here, the total variation distances, would have to be the distribution of the data or the swap data, even if you saw the weights. So if the weights depended very weakly on the data in some perhaps private sense, then you could still have this total variation distance be small. Like I can't tell which data point is which, even after you tell me what the weights are. But that's kind of unsatisfying because we would really like to be able to say that the weight is just like some function of X that tells me I'm lying in this region of space. And going back to a previous question, if you're looking for local coverage, that's exactly one of the main routes towards that is to use these X-dependent weights. So to some extent, these are right now, I feel, two branches of research that clearly need to be connected, but we don't really yet understand how that's going to work. So I would say that at least theoretically, this is an open question that I'm still very confused about at the moment. So yeah, that's a great question and a very important point.
So we probably don't have time for more questions. Thanks again for coming.